All right, let me show you what I'm doing here. I want to make sure that this fits in the part that's over there, the big piece of plate, because it's got a notch milled in it, and it's gonna fit in here and bolt into the. We're gonna drill and tap some 3/8 16 holes here for the screws, but I want this profile to fit in the already milled notch in the plate, and it's important that it fits nice and close. So I want it about 1/1000th of an inch clearance on it. So I rerun the finish cut a few times to get this down to this dimension, which is it's going to be 4.390 is 90 is more or less the dimension in the plate, but it's actually, I've checked it, and I'm going to show you how I check it to make sure that I'm fitting, because it's actually it's 1/1000th of an inch under 390. I don't know if you can see that, Mike, but this is miking about 2/1000ths of an inch under 4.390. And I check the other thing. What I do is I check it with some gauge blocks, and the width of this, the nominal dimension that I drew was 4.390. But I want to check it to see what it actually is, so that when I mill that part over there, I know it's going to fit in here. Otherwise, I'd finish that part and then I'd have it out of the machine and I couldn't recut the surface, and I don't want to set this back up to recut this, so I want to make sure everything fits. So what we're going to do is take some gauge blocks and check this. I'm going to take the 4-inch gauge block here. I'm going to take a 1/4 inch gauge block, and if I subtract a quarter from 0.390, I'm left with 140 here. But I already tried this, and I know that this doesn't quite slide in. But just to demonstrate it, I'll show it. Okay, ring these blocks together, and I tried to fit this in here, and this would have been the ideal dimension, but it doesn't really go. So I tried the 1/1000th of an inch. This is the 140,000th gauge block. So I'll get the 139 is what this is. I'm gonna ring that onto here, and this, it's kind of tricky to get in here, but it does go. Just like this would be the absolute maximum size that would fit in here. You can get it started. Now I can't do it because I'm recording it on video, but it's a little bit awkward to get this started in here, but it will go. Okay, there. So that goes, but you can see it's like snug, but it does more or less fit all over the place. You want to be sure and check it up and down, because you can get deflection on the end mill that you milled this with, of course. But it is actually pretty darn straight, but it's right at that size. And I want to have a little bit of clearance just to make sure. So let's go 1/1000th of an inch less than that. The 138 gauge block, which will be 2/1000ths under the 4.390. And that goes quite nicely. So this is what my target point for over there in the lathe. That way I know that this is going to fit together. So I check it with my mic here. I can do this. And I know that my mic is going to measure this size. So when I go over to the part, looks like the mic is measuring about 2/10,000ths less than the actual size. But I know if my part fits in here between that 4.39, 389 to 4.388 that it'll fit in this slot. So I'm not like having to recut something. So that would be really a problem, having to deal with, you know, these big pieces like this. So this is the way I make sure, because of course this plate, you know, is a big piece of material, and I don't want to be moving it around and trying it. I want to make sure it goes together without having to do that before I cut that part off the machine. This is the width we were wanting to fit to that piece of plate over on the pallet. Let's see what we actually are right now. Yeah, I don't know if you can see that, make that out in the video, but it's right at 4.388, and then maybe 1/10, 1 or 2 10,000ths right there. See what it is up here. It's the same right there. Let's check it down at the bottom here, because we could be getting some push off on the end mill. Actually, it's just a couple of tenths smaller at the bottom, oddly enough. Maybe that end mill is not ground perfectly straight. Usually it's the case that the end mills get being pushed off, and you want to make sure we check this all over. I don't think I got a good reading there. Kind of hard to mic backwards like this. It's about the same. It's pretty darn straight. Okay, so we know that that will fit in there, because you can see that the plate actually fits on this direction because of the notch with the radiuses. And this area out here sticks the center for the Mazak, the live center in the tailstock, is going to fit in here in this taper that I've turned right here on this end of the part. So this is going to be facing outward. So we know that's good. So now we can finish drilling the holes, and then this part's going to rotate around, and it's going to rough in the angle on the other side. And I'm going to finish that when it's all bolted together on the plate, when I've got it between centers. That angle isn't critical at all. It's just clearance, in case the milling tools need that clearance when we're actually machining the part. I'm looking over there. All right, I want to break into this video right here a little bit and talk about tapping. Seeing as I mentioned it in a note there that I forgot to take the peck off the tapping cycle. I want to talk about that and some other things about tapping in CNC machines in general. Now, the type of taps I generally use either this type of tap, which is a spiral point plug tap, or a spiral flute bottom tap in these kind of geometries here. I can't remember ever using a tapered tap except maybe an Acme tap, which has the taper tap built on the end of what you might call the finishing tap. So it's kind of a double tap on an Acme thread, and in general that's only good for a through hole. It's not going to work for a bottom, a blind hole, and you're going to have to either turn or mill the thread on an Acme thread type of situation. And otherwise, I don't see why anybody would ever use a tapered tap on a CNC machine unless the material was a through hole and it was a very difficult to tap material. Maybe, that might work. Now, this tap, of course, pushes the shavings ahead of the tap as it goes in, because the spiral point on it tends to push the shavings ahead, and it works good for a through hole. Although I have and tend to use these a lot for blind holes as well in tougher materials, because the tap is stronger and it'll take more torque on the tap, whereas a spiral flute tap like this, as you can see, the flutes are machined into the shank, and it has less strength than this tap does as far as out at the tip of the tap. Also, in smaller sizes, these are 1'8" taps, and they're very large, and you wouldn't have this trouble. But in smaller sizes, like this is the same size tap I'm using in the video here on this, and this is the spiral flute version of it, which is what I'm using in this video, and the plug spiral point version of it. Now, I have found on trying to do this peck tapping like I'm doing in the video, although the aluminum is so easy to tap that it doesn't cause a problem, but if you're tapping more difficult materials, that this type of a tap will tend to torque up, so it'll actually twist the shank a very small amount on a smaller sizes like these sizes, and it won't do it enough to break the tap. But if you go in a certain peck depth with the load of the normal tapping on it, and then you come back out and then you go back down that thread, and before it gets some load on the tap, it's going to kind of skim the thread off a little bit, and in these cases I have found that the no-go gauge will start in the hole if you try to do that with this style of tap. So generally speaking, I don't run pecking on tapping if I can help it. And then if you can get to the, like, open the doors of the machine, I can't do this on the Mazak, but on the horizontal mill I could. And if you could blow the shaving off the tap, like if you're using a spiral point plug tap like this, and you're going in a blind hole, you could probably blow the shavings, because it'll tend to pull the shavings back with it a lot of times, or on the flutes, and you can blow them off and maybe even squirt some additional tapping fluid as you're going back and forth if you're doing a like a very deep hole maybe, and that could maybe work. In the case of these, like I said, for the other reason, unless it's a big tap like this, you're not going to have a problem. This is not going to torque up too much in a hole. So that's the styles of taps I use, and kind of my reasoning though I had this question in the shop here. A machinist came and asked me this just the other day, and I thought I'd talk about it a little bit. How do you figure out what speed and feed to run a tap at? And over the years, this is kind of what I've settled upon. And one of the reasons I kind of learned this lesson a long time ago, that people tend to run taps too slow. And I was tapping not this size, but the size under this, a 7/8 9 thread. This is a 1" 8, and it was the same kind of tap, and I think it was even this Imugi tap brand, and it was chipping it was chipping the flutes of the tap back here on the flutes, and for the life of me, I couldn't figure that out. I said, why would it chip the flutes back here? And I talked to the sales guy that sells the taps, that represents the taps, and he told me I'm running the tap too slow of surface footage. And so when I sped it up, it actually cured that problem of chipping the flutes back here on the end of the flutes, actually, which is kind of weird, but it did. And this was probably, I don't know, 20 or 25 years ago. I kind of learned this lesson, that you don't necessarily want to run taps too slow, because that's just as hard on the tap as running it maybe way too fast. And depending on what the machine's capability is to synchronize the thread, this is what I learned a long time ago. And I had this exact question last week from a machinist, and I said, he said, how fast do you run the taps? And this is what I generally do. I go 40 inches per minute in materials that are a little bit easier to tap, like say aluminum, mild steels, or stainless steels, ductile materials that are easier to tap. And when it gets more difficult, I might go down to 20 and then down to 10 in extremely difficult materials like maybe Inconel or something like that. Although I generally rarely ever use 10 inches per minute. I stick around these 40 and 20. Now, I know it sounds kind of strange, but why would you relate the feed rate to what you're doing with tapping? Well, of course you have to synchronize the feed rate, but let's take an example like this tap is a 16 pitch tap. So in inches, that means you're going to rotate 160 RPM for every 10 inches per minute feed rate. So at 40 inches per minute, what's that work out to? Is that like 640 RPM? Yeah, I checked it here. It's 640 RPM at 40 inches per minute. Now, if you're dealing with a 1" 8 tap, it's going to be 80 RPM for every 10 inches per minute feed. So the speed at 40 inches per minute is going to be 320 RPM. It's going to be half the speed of this 3/8 tap, and this has been working out for me over the years to use this relationship of feed rate, and don't think about RPM so much as feed rate, and this will automatically control the surface footage the tap runs at, because you got to synchronize it, of course, between the speed and the feed to get the the threaded hole in there. So this is what I've always done. So 40 inches per minute has always worked out to be a good rule of thumb in steels, mild steels, aluminum, stainless steels of some sorts that are ductile materials. Now when I get up to maybe titanium or Inconel, I'll slow it down to 20 inches per minute. And you could calculate the surface footages, and this will work out just about right. I know it sounds strange, but that's what I've always done, and this is what's worked for me since I kind of learned this lesson with the Imugi guy about the 7/8 9 thread, because I had tended to run stuff too slow, down like 5 inches per minute and things like that, and generally that runs the tap at too slow a surface footage, and it doesn't cut as well, believe it or not, even though it might seem, with these arms and stuff people run this tap kind of slow, but in general you want to run the tap faster than you might think. So that's my little quick explanation of tapping on a CNC machine. I mean, there is more to it than this, of course. There's form taps and various other kinds of taps, but These are generally the two styles of taps that I use most of the time. Might need to get the Sawzall and cut that. I didn't want to make that too thin because it would vibrate. But it's a little bit too thick to break off. Didn't really like the way I had this programmed. I didn't have clearance moves coming up. It was rapiding through here, so I slowed the rapid way down because it was actually hitting the end. You can see a few of these spots where it hit the end mill in a rapid movement. This is going to be finished when it's bolted to the fixture, when I get it between centers. All right, let's see if this actually fits in here. Might be easier to set it down here and start it like this. It's actually going to go on the other side. This is the wrong side facing up, but it fits in here all right. So that's the way it's going to go, except on the other side of the plate, because the holes are on this side. The holes are on this side for the cap screws, so it's actually going to go on the other side of the plate, but it does fit in there. See, that's the reason I wanted to check it with the gauge blocks before I took everything off the machine. Make sure it all went together. So that's this part. Now we got to make the one that goes down for the other end of the plate, and that one actually chucks in the spindle. This one rides on the tailstock center.